Okay, so finally made it to the last part of 6.1. It's kind of a packed section. And I just wanted to do some examples that match what the book work is like. So we did some that matched AP Test. Now I wanted to do some that match the book because they're excellent practice. And it just kind of will confirm what we've learned in the previous sections. So here it's asking us to solve the initial value problem, which we know has the 5 steps. And then it wants us to support our answer by overlaying the solution on a slope field. So we're going to make a slope field, solve the differential equation, and then graph our solution onto here. So maybe I'll just start with the slope field, and maybe I'll do that over here. Notice it only has x's in it, which is really nice. So I just need to plug in x's. I don't need to worry about y's. So I'll just go from -3 to 3 again, like the last one. So I'll plug in -3 for x in here, and I would get 1/9 minus 3, which is -2 and 8/9. And then plug in -2, which would be 1/4 minus 2, which is -1 3/4. Plug in -1, which would be 1 minus 1 is 0. Plug in 0, and we have a problem, undefined. So that'll be vertical tangent. Plug in 1, and I'll have 1 plus 1 is 2. Plug in 2, and I'll have 1/4 plus 2 is 2 1/4. And plug in 3, and I'll have 1/9 plus 3 is 3 1/9. Okay, so let's go ahead and plot all of these slopes. So at -3, I'm going to have a negative steep slope. At -2, I'll have a negative less steep slope. At -1, I'll have a horizontal slope. At 0, I'll have vertical slopes. At 1, I will have positive, somewhat steep slopes. And then at 2 and 3, the slopes get more steep and they're still positive. So there we go. All right, now let's go ahead and solve the problem using our 5 steps. So I'll begin by separating the variables. As we know, that's extremely important. Then I will go ahead and integrate both sides. And all the while remembering that there is a 1 right here. So when I take the antiderivative of that, I get y. And maybe I'll think of this as x to the -2 plus x. So the antiderivative of that would be x to the -1 divided by -1. The antiderivative of that would be x squared over 2, and then don't forget the constant. Okay, so now I want to plug in the initial condition. So right here I'm given the point 2, 1. So I'll plug in 2 for x and 1 for y. And I'm going to rewrite that as -1 over 2. And then 2 squared over 2 plus c. So I get 1 equals -1/2 plus 2 plus c. So 2 minus 1/2 would be 1.5. And then 1 minus 1.5 would be -1/2. So I get that c is equal to -1/2. And so then my last step would be to solve for y. So I get y is equal to -1 over x plus x squared over 2, and then -1/2. Then they want us to graph this on top of that slope field. So we could either plug in, like do a table of values, we could see what's happening to this equation as x gets really small, those kinds of things. Or we could sketch it on our calculator if we had that available to us. It ends up looking something like this. First of all, we have this point 2, 1. So we want to use the point available to us. And it kind of ends up doing this sort of a shape here. And we actually have a vertical asymptote right here where we had the vertical tangents. And by the way, when you have vertical tangents, that's what that is. It's from a vertical asymptote. And then on this side, like for example, if I plugged in the point -1 into here, I would get, if I plugged in -1, I get -1 over -1 plus -1 squared over 2 minus a half, so I'd have 1 plus a half minus a half, so I'd have 1. So I have 1 point, which is -1, 1, so kind of is like that. And then I can sort of follow the slope fields, and it would do something like that. So it's going to go up. Oh, and the way that I know it's going to head up to positive infinity is if I looked at this expression as x is approaching 0 from the left. This number would be negative, and it would be huge. No, excuse me, it would be positive. Sorry, because I'd have -1 divided by a tiny negative number. This would be a huge positive number, and these would be both small numbers. So this huge positive number would totally outweigh those small numbers and end up becoming positive infinity. So that's how we can see that it's going to go up here instead of down there. Whereas on this side, if x was approaching 0 from the right, it'd be a teeny tiny positive number, which would make this a gigantic negative number. Because I'd have -1 divided by a teeny positive would make this a huge negative. And so it'd be so big, so negative that it would swallow up anything that this is and make the overall value a really low negative. So this side's going down to -infinity and this side's going up. And we really were able to just sort of use this point and the direction of the slopes to get that. And the fact that we had a vertical asymptote at 0 as well. Okay, so that's example 1. Example 2 is similar. It says, here's the velocity. So they're giving us a rate of change of a body moving along a coordinate line. We've seen a lot of those moving along a coordinate line type problems. So here's the velocity right here. And now it wants us to find position. So right there, we know that's the antiderivative. It wants us to find position, which is the antiderivative. But not only any position, but the one that has a point at 1, 0. So basically, this is an initial value problem because I have to find an antiderivative and plug in initial value. So we'll go ahead and follow the 5 steps. Step 1 is, well, first we need to recognize that velocity is the derivative of position, ds dt, is equal to sine of pi t. Because the derivative of position is velocity, so I can swap this out where the v is. Then I want to separate my variables. It's very important. Then I want to integrate both sides, all the while remembering that there's a 1 here. And then I get s on the left. And then I have to take the antiderivative of sine of a constant times t. So a little memory bubble over here, we're going to use this formula. When we're integrating sine kt, it ends up being negative cosine kt divided by k when I take the integral of that. And then, of course, plus a constant. Hold on. That looked weird. Okay, so plus a constant. So this ends up being negative cosine pi t over pi plus a constant. Okay, now here's where I plug in my initial condition, which is 1 for t and 0 for s. So this is 1, 0. So I'm going to plug in a 1 where the t is. And that's basically just cosine of pi. And cosine of pi is basically -1. So I have negative 1, which equals positive 1. So I have 1 over pi plus c. So let me move up here. So then I have 0 equals 1 over pi plus c, so minus the 1 over pi to the other side, and that's what my c is equal to. So then the final answer, which I will write over here since I have more room, is s is equal to negative cosine pi t over pi, and then minus the constant 1 over pi. And that is the body's position at time t. When they say at time t, they mean they want t in the answer. That means I should be able to plug in at any given time and find my position. And so here will be the body's position at time t if it passes through the point 1, comma 0. Okay, then for example 3, these are just all examples from your book. You're given the slope field and it just wants you to draw a graph for the function. Doesn't give us an equation or anything. Just gives us this point, -1, -2. So I locate -1, -2. So left 1, down 2. And then I just follow the directions of the slopes. Looks like here they're tending down. And here they're kind of going up and then back down. So this kind of looks like a parabola again, like the first one we did. And that's pretty much all you do. And that's all you can do. And the answers might differ a little bit, but you do want to make sure that you have the point that they specified clearly shown on your graph, and then from there you just follow the slopes. They don't have to touch the slopes, they just have to follow the general direction of the slopes. Okay, then for the last video we will do the second page of part 3 of 6.1 notes.